So my name is Harinandan. I'm going to be demonstrating theory of relativity by Albert Einstein. Most of you people should know what theory of relativity is and who proposed it. It was Albert Einstein in it's 1915. So the theory states that if you space is like a small fabric, and when you put a heavy object that has like heavy mass, it will bend. So you can see there it bends. So now by creating that curvature there, it creates like a small field where it will create an orbit. So if you put multiple objects in orbit, I'll show you. Just keep orbiting. Also, in our solar system, many of the planets are like it won't. It's always going in the same direction. I'll show you. If you put two marbles and just throw it in two different directions, you can see it will eventually collide and only some will remain. So that's why most of the solar systems have more only the planets are moving in only one direction. Next, let's talk about the moon and the solar system. Let's take this. Right. So let's see. Let's take this as a moon and this as the Earth. You can see that if I move my hand, you can see it keeps rotating. Like it will go around it. Instead of like staying in a place due to this curvature, everything gets attracted. So this many of the people have a misconception that Einstein proved Isaac Newton wrong, but it's not true. Einstein just drew a bigger circle. So basically, for smaller objects like from Earth, the Newton's formula is correct, and for larger objects like black holes, Einstein's formula is correct. So I'll demonstrate how a black hole works here. So let's imagine this mass and this this is like let's imagine its density to be 5. With the same mass, its density will be 1. So basically, it will cross a point where the density becomes so high that the gravity is can see. We have to push it down really hard to notice it, and anything we drop near it will go inside. So many people have a misconception that black holes have infinite density. It's not true. It has a specific density, but it's not. It's so high that we feel like it's infinity. So we also know that there's like time dilation and stuff. So basically, this happens. If you put an object, we go near it. Let's take this, and it's here. Instead of traveling this distance, we will have to travel this. So time space is space time. So it will also have time. It will like bend and produce like a small delay in time. That's what time dilation means. Also, there's new concepts like gravitational lensing, and it's basically like let's explain simple terms. So these are photons. Let's imagine, and we take this as a source, and it's coming from the source. Let's take this and this out in a straight line. You can see instead of going from here to here, it went from here and gradually bended. So this is called gravitational lensing. It causes many distortions. You may have seen it in James Webb Telescope's new images. It causes like distortion in space time. So this is the basics of general relativity. It's like we can dive more deep into it. Like there's like quantum gravity and stuff that is very hard to understand. Uh, for a planet to have rings, this, let's see, this will go around this. Instead of colliding, it will just go around this for an indefinite time. This will cause it to have rings. This is if the rings are like small dust particles and ice particles. Instead of that, if it contains a large particle, it will be known as a moon. So basically, like rings are basically like small particles of moon. So this theory is very simple, but it will take some time to understand. Also, it depends on how you take it. You may have some doubt about it. You can ask now if you have any doubt about it.
Not yet.
Okay.
What if the host
So
star have huge mass? Like the black hole has a huge mass and it bends the curvature, like it creates a parallel universe along with that.
I think it's you're talking about wormholes. Am I correct?
Can you repeat?
Are you talking about wormholes?
Um, I don't know that. Sorry. Can you explain it?
Yeah, sure. So wait, let me. I'll show you a screen. I'll show an image. Wait. Recording. Okay, so basically wormholes are like shortcuts through space. Instead of going through a straight path, it will like make a hole in space time. Like it will bend space time in like half. I'll show you an image right now. So you can see that the line grid lines. Can you see the screen?
Not right now.
No.
Okay.
Yeah, we can now.
Yeah, you'll be able to. Yeah, so this is called a wormhole. So basically, the space time is bended to like it will like bend 180 degrees
Yeah, I'm
to
talking
create
about
a
this.
shortcut.
I didn't know the term, what the exactly term called.
Okay, okay. This is theoretical object. We haven't found yet one yet. Okay, it's there are many theories like it's a black hole is here and a white hole is here, and like
Yes.
when you travel through it, it becomes a black hole. Like it's too complicated. So these wormholes are like shortcut through space. It's the only way for us to travel such a long distance in short time. It's one uh, there's a list of things we will achieve in the next decade and we will achieve in the next probably like a million years. One of them in a million years is traveling through a wormhole. So it's like very rare to find one, and it's like traveling through it. We don't know how it will affect our bodies. Like it may crush our body into like a small dog maybe.
And some
So
some research
uh,
paper says that we have some wormholes in our universe, but they're in very small size. They're in atom size, so we can't access it.
yeah. Uh, Also, like uh, when the wormholes are like atom size, the quantum mechanics takes place, so it can move. Like we cannot predict its location.
Yes.
Also, I'll show you gravitational. You may be familiar with this image. Okay, can you see the image?
Yeah, we can.
So, so you see this. Like it's supposed to be a black galaxy this that looks like this, but due to this a galaxy being in its way of like the light, it will bend light. Also, next I'm going to talk about gravitational waves. You have you heard of gravitational waves before?
Where does it occur?
The gravitational lensing.
Yes.
So it occurs like near like, so basically I'll show you the screen once again. Okay, you should be able to see the screen now. Okay, can you see the screen?
Yeah, we can.
So
Yeah.
let's say this is uh, this is NASA's Starlink right here, and this is where we observe. Okay, so these are photons. Let's take them as photons. Just throw it. You can see like it go instead of going straight like this, like this, it go takes a circular path. So basically, like it will curve like instead of like if you observe that image also, you can see it will curve it instead of like making it distorted. Instead of making like break in some places due to this heavy mass, like since space is stretching in a circular manner, it will create like a circular curve. So that's about gravitational lensing. Now let's talk about. Have you heard of gravitational waves? Hello, can you hear me?
Yes, yes.
Are you familiar with gravitational waves?
Yeah.
So I'll explain. Let's take these two as two massive black holes, and they are about to collide. They will just circles spin on each other's gravitational fields. That will create like a entire distortion in space time that will last. So can you see this? It will create like a wave.
Yeah, I see.
Yeah. So then when the wave hits the planet, it will create like it will squish like turn it into this and then it will turn back to round shape. So just basically squish. So there's some gravitational wave detectors called LIGO detectors, and in those detectors there are like two arms stretched towards each side. If you want graphical illustration, I can show you.
Yeah, sure.
Okay. So you can see this. So this is how it looks. These are like 4 kilometer long. So it's like really long. Okay. So when there's a beam splitter here. Okay, I think it's loading. Okay, you should be able to see now.
Yeah.
Okay, so there's a beam splitter here. So this laser will produce a beam, and it will go through here. It will go through a partially reflecting mirror, which will keep reflecting this light back and forth. And there's a photo detector here. So this beam splitter is placed in a way that if one arm's length is shorter than the other, it will create a distortion and it will go. The light will be redirected to the photo detector. So
All right.
this so when it squishes the earth, it will the one of the arms gets shorter than the other. Then it will create like a distortion and it will be detected by the photo detector.
Okay. All right.
So this is how a way this was proved. The Einstein theory of relativity was proved. And the first time it was proved was with it was like uh, you guys know solar eclipse, right?
Yeah.
So in solar eclipse, yeah, in solar eclipse, the sun's light is it's the dimmest. Sun is like its light is the sun is covered by the moon, so it will not have much light. So the earth is here. The since the moon is in middle, since the moon is here, let's imagine the uh, photons from the stars from the back of the planet, like which are here, situated like here, will bend and form a distorted image. That's how it was proved first time, but it was just like it was not concrete evidence. It could still occur by some other manner, and that could be the case also. So this it was officially proved by the gravitational wave observatories. That means the LIGO observatories.
Hello.
So hello.
एक doubt है. I have a doubt.
Yeah, sure.
Can I speak in Hindi? Is it okay for you?
No, because I'm from Kerala,
Okay.
so
Let
I don't.
let me try.
Okay.
You said earlier this massive object which is Earth is rotating. Okay,
Okay.
and the moon is also rotating with the Earth
Yeah.
with the same speed, right?
Yes.
If uh, if we increase the speed of Earth like the
Mm.
faster than the light speed of light,
Okay.
what will happen to the moon? It also increase or go out of the space?
Yes, it will go because the moon will not have like, enough time to react to the gravitational waves. Like if
Oh,
I just
okay.
go, you can see. And there is problem. So let's take this as a moon, and this as the, and if I move it really fast, you can see it will get thrown out of the orbit uh, instead of just going uh, like staying there, it will go out of the orbit and just throw it away.
Okay,
Like
okay.
so basically that's Voyager 1, right?
Sorry.
Voyager 1 spacecraft.
Okay.
So the Voyager 1 spacecraft uses the same technology. So
Mm-hmm.
this it was demonstrated by Saturn. So basically Saturn is here. Let's imagine this is Saturn and this is the Voyager 1 spacecraft. The
Okay.
instead of going with like not touching the Saturn's orbit, it went here, and due to this moving, it gets an acceleration to go forward.
Mm-hmm.
I'll show you. You can see that. If I just throw it with the same force, just go there.
Yeah,
But
yeah,
if
yeah.
I put this object and it's moving, then you can see that. So this is
Okay,
how
okay.
Voyager 1 traveled. So
Uh-huh.
so this is all about general theory of relativity. If you have any doubts, you can ask.
By the way, I'm just curious about that. If we place two black holes facing each other, then what will happen?
Okay. The black hole having the larger mass will absorb the other one. The black holes will become like, so black hole is like a heavy a object with so much mass, it becomes like it will crush into its own gravitational field. So this star, let's imagine this is a rock, okay, and we make it into sand, okay. Then we add water to it. We can just make it a smaller version of itself, but with like smaller size. You get it?
Yes.
It will be the same mass but with smaller size. So basically, density becomes higher. That's how black holes are formed. So this star will turn into dust, and
Okay.
due to it having the same mass, it will have the same gravitational field. So
Hmm.
and it will turn into a smaller one with the same mass. A question arises, like just curious question about this
The size will vary, but
phenomenon.
the mass will be the same.
Yeah. So if there's a question, if we replace uh, sun with a black hole, the same mass as sun, will it absorb the Earth?
I
So
think
can
no,
any
because
of you guys?
it has the same gravitational field as likely as sun. So I don't think that it will
Yeah, exactly.
or something like that. Because it will not bend the space curvature now. If it has the
Uh,
same gravitational field as sun.
yes, it will not bend it further than the it's because it's having mass. Density doesn't like the size doesn't bend the space time. The mass does. That's the answer to it. The correct answer. So if you guys if any of you guys have doubt, you can ask.
So if the mass of black hole is greater than sun, the black hole will absorb, swallow the Earth.
Yes, it will. It will follow that.
Okay, okay.
So let's take it with an example. So this it's going towards it's rolling around sun. Let's increase its mass by just putting a pressure. Yeah, you can see it will eventually come inside. Like if I doesn't apply that force, it will go around. So this in this in this project, the planets are going towards the center is due to friction and air resistance. In vacuum of space, there's no friction and air resistance, so it will not. It will just continue rotating due to inertia. It will not need any energy. Any more doubts?
No.
No.
Okay. That's it.
Okay, so can we end the meeting?
Yeah, yeah, sure.
Thank
Okay.
you.
Thank you, Harinandan, for joining us. Thanks a lot.
Yeah, welcome. Thanks for having me.
Thank you so much.